Okay, so in this first question, what we want to do is to design a round robin arbiter. It is a parameterized arbiter, but for now, let's just focus on n is equal to 4. That's the
Mhm.
first step which we will do as part of this question, and then see that how we can improve our design from there to, for any number of n. And I'll quickly explain like what are the ports definition here for the module. So you have like a clock and a reset given as input, and then you have 4-bit input, which is the request underscore I, and this tells the 4 different ports of the arbiter. So this is the request underscore I input, and then on the same cycle you're expected to produce the grant output. This is grant underscore O. The thing which is associated with the grant output is that it is a one hot uh, vector. If the request underscore I is non-zero, if it is 0, then it is 0 also.
Hmm.
And the way it is produced is that on every cycle you use the round robin algorithm to generate the next grant. So I'll walk you through how this is supposed to work for a few cycles. Let's say this is cycle 1, 2, 3, 4, and 5, and these are our request input, and this is the expected grant output. So let's say this is request port 0, this is request port 3. Similarly, this is grant port 0 and grant port 3. Now, right out of reset, we will give more priority to the LSB port. So
Hmm.
let's say that the incoming request was 0110, right? So in this particular case, since we are giving more priority to LSB, what will the output be? It will basically be 0100,
Hmm.
because the arbiter would have given grant to port 1 here.
Hmm.
Now let's say in the next cycle, we get our input as 1100. Now, as per the round robin arbiter, we should have given grant to this port
Hmm.
because we are moving to the next one. But since there is no request here or here, what will end up happening is that the grant would be given to this particular request here, because that's the next. I mean, again, giving more priority to LSP stuff if the round robin arbiter does not find any of the other ports having any request. So
Hmm.
the output in this case would basically become 1000. Now let's say that on these cycles we always get 1111, 11111, and so on. So now since we had given grant to this, in this particular cycle, since we have request on each of the ports, it will actually work in the round robin fashion. So
Hmm.
now on this cycle, it will be 0100. Then on this cycle, it will be 0010. And then here it will be 0001, and so on.
Hmm.
Right? So this is how it is supposed to work, and you're supposed to design the logic for producing the grant underscore O output. Assuming that for now we only have 4 request ports, and then we'll see that how we can change the logic to work with any number of given ports.
Hmm.
Any other questions?
Uh, Not at this point.
Sure. Okay. Okay. So I'll request you to share your screen, and then we can.
Sure.
Yeah.
Um, what I'm thinking is I would have to look at the incoming request, but at the same time, I would also need to have some mechanism to keep a track of which was the last granted request in the previous cycle, so
Mm-hmm.
that I can decide which request do I need to start looking from in this cycle.
Sure.
So, uh, yeah, so let's say this is my request and it's a 4-bit request.
Mm-hmm.
Um, yeah, so this is the request. And uh, so your first example, I think it was, don't remember,
00.
1100. Yeah.
Sure. Mm-hmm.
Uh, so initially, my last, so I'll have a flop, like I'll have a uh, 4 flops basically in this
Mm-hmm.
case, but that will be my last granted it will keep the status of which was my last granted request. So in the
Hmm.
beginning, I did not see any request, like it's out of reset, so my last grant is 0.
Sure.
So my thought process is that somehow using this last grant, I have to create a way to mask some requests. So using the last grant, I will create some mechanism that will mask some of the requests.
Hmm.
Uh, so basically, what I'm thinking is, uh, if I have a mask, if I create a mask from my last grant,
Hmm.
um, so I'm thinking that once I have granted something, let's say, in this case, I have not granted anything, but once I have granted something, so bit 0 is the, or request 0 is the highest priority. Um, and so let's say if in some cycle I have granted this request, we will see that in the next cycle, but when I grant this request, what it means is that in the next cycle I want to start looking from request 3 onwards.
Right.
So from
Right.
request 3, and then if there's nothing, then I loop back and look at request 0, request 1, request 2, in that order. So
Hmm.
basically, starting from my MSB of the last grant, I am trying to see which was the uh, which was the request which was granted, and
Hmm.
anything below that bit position, I won't look at it unless there is nothing in the other request. So what I'm saying is, start from the MSB to create the
Hmm.
mask, copy over this bit 0 of the last grant, and
Hmm.
I'm trying to find a 1 here in the last grant, and then everything after that will be 1.
I
And
see.
I'll create a mask, like I'll negate that to create a mask. So in this case, there is no 1. So my 0, and then I'll OR it with this. So 0 or 0, and then 0 or 0 is 0, 0 or 0 is 0. So
Hmm.
yeah, so this is actually my mask, meaning none of my requests are masked. So I'll use
Hmm.
the negate of mask, and yeah, so that will be 1 1 1 1, and I'll AND that with my request vector.
I see.
So this will be my actual like request vector that I will use internally. So
Hmm.
I AND that with my request vector. So it is what, 1 1 0 0.
Right.
Now, this is the request vector I want to look at.
Hmm.
And starting from the lowest bit position, I will try to find the first one and then create a one hot out of it, one hot grant vector.
Sure.
So my grant vector, again, it is copy this over, and yeah, and then for this one, yeah, so uh, 0, right? Zero, this bit position 0, and like nothing. So basically, what I'm trying to find is if this was 1,
Hmm.
uh, then this is like the first one. I mean, there was no other one seen
Before this.
before. Yeah.
Okay.
So
Yeah, that makes sense. Hmm.
this bit, and there was no other one, would be my
Hmm.
logic for every bit after the 0th bit. So I copied this over as is, and then for this bit position, this is not 1 in this case, so 0 and anything is 0. In this
Hmm.
case, this is 1,
Hmm.
right? So 1, and there was no other 1 here, so this
Right.
is my first one.
Sure.
And then when I come to this is 1, and this will not, like, no other 1 will be 0, so this will become 0. So this will be my grant vector.
Sure. And this would be
Then
the actual output.
this will be my grant output, actual output. Yes.
Okay. Yeah,
Now
so
in
couple of questions. Sorry.
yeah.
So the first thing which you said that you will traverse the last grant from MSP position onwards
Hmm.
to generate the mask for the current cycle. So
Hmm.
why is it from MSP? I did not understand that part. Could you
Yeah.
explain that?
Yeah, so let's go to the next one, and that will probably explain.
Hmm.
Uh, yeah, so now this grant vector is going to be my last grant in the next cycle.
Correct.
And what was your request in the next cycle?
So let's say it is 0011.
0011.
Yep.
Okay. So basically, the idea here is that uh, this was my last granted request.
Hmm.
So I want to start searching from here
Okay.
for the request. Anything below this index position, I am masking it for now. Like if
Hmm.
this is requesting, then I want to look at that, not anything below that index that is requesting.
Sure. So
Right.
a question here. So you would basically figure out the index of the last grant also, or how would that be done?
Index of the last grant.
So you said that in this example, right, the
Uh,
one would be at the MSP position because the grant was given on the bit position, one bit less than the MSP, right?
yeah, yeah.
So let's say if it was given on bit one, if the grant was 0010, then how would the logic work? Like, how would you figure out that where is the one in that last grant?
Yeah, so in let's take this example.
Sure.
Uh, so in this case, how am I generating the mask out of this? So I
Hmm.
copy this bit position 0,
Okay.
and 0 or 1 is 1.
Okay.
Then 1 or 0 is 1.
Okay.
1 or 0 is 1.
Hmm.
So my mask is actually 1000.
Sure.
And now, okay, now is like the part where, yeah, I'll have to think through what happens here. But basically, this is my mask. So what I'm saying is, if this is requesting, request 3 is requesting, then
Hmm.
that is what I will prioritize, because previously I granted request 2. So I want to start looking from request 3. So
Agreed. Yes.
when I AND these two, now my request vector actually becomes like, there's no request here, 0000, right? So
Hmm.
it actually ignores these two requests.
Hmm.
So yeah, in this case, the mask won't work. Or I have to do some logic where if I'm seeing that there is nothing in the masked request, like if there is nothing in the masked
Hmm.
request, then I pick the original request. I go back to the original request. So maybe like a mux that sees if there is anything in the masked request, then I pick the masked request. Otherwise, I pick the original request for
Sure.
my request vector. So this will be my request vector. Yeah. So now, yeah, so I should probably call it masked request here. And this is 0000, and in this case this is 1111100. So my request vector now, after the mux logic, will, because there is nothing in the mask vector, I'll pick the original request as my request vector, which is 0011,
Hmm.
and then apply the same one hot logic. So one copies here, this is 0 because 1, and I've already found a 1, so, and then 00, right?
Right.
Yeah. So, and then in the next cycle, this grant vector will be my last grant. So this I'll use for generating the mask.
Yeah. I think I get the idea. Like, should we try coding this out?
Sure.
Yeah.
So yeah, so with this design, actually, it lends itself. easily to be parameterized. Uh,
Okay.
so, but I can write it without the parameter first, and then we'll see how to parameterize it.
I mean, it's
Um,
up to you. Like, if you're comfortable writing with the parameterized design, then I would recommend doing that.
okay.
Hmm.
So, what are my intermediate signals? Let me define those. I have last grant, and I have my mask. Um, and I have masked request,
Hmm.
and I have my request vector and my grant. One hot, or you already have a grant, so that's okay. Um, yeah. So, uh, I typically use always comb.
Sure. Okay.
Uh, so let's see. I mean, I'll do the initial assignments. Yeah. So before we get into this for loop where I'm going to generate the mask from the last grant, and
Hmm.
yeah, I have to create a flop for the last grant. But let's say um, I generate the mask, right? So my mask is yeah, like I can just zero it out, or I can say tick zero, or yeah, like n1 tick p0.
Hmm. Okay.
Um, so that is my mask, and that's what I will be finding out here. And yeah, let's see how I generate the grant vector, and I'll keep adding to this as we go. But before that, let me create a flop for the uh,
Okay. So you're using asynchronous reset?
yeah.
Okay.
Okay, so
Mhm.
that's my last grant. Now, uh, mask zero is, sorry, I'm starting from the MSB actually. So, uh, yeah, then I should change the way I'm iterating through the loop also. Okay, so
Mhm.
yeah, this is that part where I'm going to um, just copy over the MSB, and then, or like for this bit, I will generate this, or this is this, or this is this, or this is this. So
Sure.
that's
Mhm.
what I'm trying to do here. Um, so my mask of I is mask of I plus one,
Mhm.
or uh, or last grant of I. Right,
Okay.
that's what my logic does. So this is
Mhm.
how I generate the mask.
Sure.
Uh, yeah, and then I need to find out what is my request vector, which I'll be using. So uh, let's say my mask request I'm going to assign here. My masked
Mhm.
request is my request that came in, and uh, my, because like this is my mask, but uh, I need to AND it with, so it's 000 here, right? But I need to AND it with
Mhm.
the negation of mask. So
Correct.
So that's what I'm trying to do here to generate my masked request. So, so this is my masked request,
Mm-hmm.
and my request vector. So now I'm going to create this mux here.
Mm-hmm.
So um, my request vector is, if there is anything in my masked request, then it is the masked request. Otherwise, it was the original request that came in.
Right. Mm-hmm.
Okay, and yeah, now for my grant logic, yeah, I would also I would do that again inside the always com, but I am trying to learn how to use the Genvar from your, which I learned from your course.
Sure.
So
Give it
let
a shot.
me, yeah, let me give it a shot. Uh, I'm not sure actually if I use I here and I here, will it conflict? So let me just use J just to be safe.
Sure.
We'll probably start from one, right?
Hmm.
J is equal to J plus 1, uh, begin, uh, end, and but before that we want to, so grant O of 0 is, um, so I'm looking at the request vector and just
Mm-hmm.
copying bit 0 as is. So bit 0 is the same.
Correct.
Uh, so this is my request vector bit 0.
Mm-hmm.
And then starting from bit position 1, uh, grant of J is, um, if uh, if this bit if this bit was 1, then this is only 1 if this is 1 and nothing before it was 1.
Correct.
So request vector of J and uh, request vector of J minus 1 is to 0,
Mm-hmm.
and right,
Mm-hmm.
yeah.
Yep. Yep. I think that should do it.
Mm, yeah,
Yep.
I think I have all the portions. Mhm.
Mm-hmm.
Yeah, but I'm aware that there are many ways to design a round robin arbiter. This is something that I learned. Uh, yeah, so
No, I think this looks good, but just a follow-up question on your approach, that what do you think would be the worst path here, or like the timing critical path for this particular design?
hmm. Okay, so let's see. I am looking at the request coming in. How do I generate the masked request? Um, so I have the last grant here, which are flops,
Mm-hmm.
and from the last grant, I am using bit one of the mask is last grant one. It's directly coming from the flop, so that's
Mm-hmm.
mask one, mask n, and then
Mm-hmm.
for every other bit it's an or, right? So I have an or of the last grant, this bit, and the previous bit of mask. So whatever was this, and the next bit is getting odd,
Mm-hmm.
and then again over here, this one is going to come directly from a flop, but this one is getting odd. Yeah, so for a level, like for 4 bits, there are 4 levels of this ORing
Mm-hmm.
that are happening here. So this is my mask, and then after that, I'm inverting all of the bits. So there is an inverter here. Uh, and yeah, the mask request going into the mux is a long path,
Right.
especially for the this bit 0.
Hmm.
So yeah, and after that I'm going to use this and it with the request.
Correct.
Yeah,
Followed by a mux, and then
followed by a mux.
and then the final find first there.
Yep, yep.
Mhm.
Yeah, so yeah.
But I think one of the good things here is that if you take a look at bit 0 for the masked vector, right? So
Mm-hmm.
it has like all of those. I mean, the fan out is right from bit n towards the bit 0,
Yes,
where all of the
yes.
orders are. But if you take a look at your find first approach, that does not have any logic on bit 0. So it does the other way around, right?
Mm-hmm.
So that
Mm-hmm.
is
That's right.
that in a way is better for timing, because now you have distributed logic accordingly. You know that your masked bit n
Hmm.
comes directly and does not have a lot of logic there as compared to bit 0. But then on the other side, if you take a look at your find first, that will have like all of those OR gates again and the AND gates on the last bit n.
Hmm. Hmm.
Because the find first would work from bit 0 all the way to n, so the nth bit would have like all the previous logic included
Yeah.
into it.
Hmm.
Okay.
Yep.
Yeah,
Yeah.
but in a way it's a nice way to design this, because the logic is sort of equally distributed between the two bits. Yeah.
Mm-hmm.
Mhm.
Yeah. What would be a different approach to designing this?
So there are multiple ways to do this. I've seen people who generate the mask
Mm-hmm.
directly in the same cycle and then flop it and use it, so that they don't
Hmm.
have to do this, the all of the OR gates which you see there. But then
Hmm.
that adds on to the grant.
Latency. Mm-hmm.
Yeah, on the grant. So because
Yeah.
now the grant would actually have some more logic after it is generated. But
Mm-hmm.
yeah.
Mm-hmm.
And then there are
Okay.
various techniques to do the find first and using a parallel prefix algorithm, where instead of
Mm-hmm.
having all of those OR gates, it'll just have like it'll do a lot better in timing. That, but yeah,
I see.
I think this is I think this is good.
Okay.
Cool. Okay, ignore the whatever the text is here. I'll try to explain what the problem statement is.
Hmm.
So so let's say you are designing a particular module where you have a counter which is 64 bits,
Hmm.
right? And let's say it gets incremented and decremented with some way internally. And what you're supposed to do is, again, you have a single clock and reset. You're supposed to read the value of the 64-bit counter. However, the read side only has like a 32-bit bus. So let's say this is valid output, and this is the count value, but this is a 32-bit bus. And let's say it comes in as a request also. So the read interface would give you a request, and whenever you see a request as asserted on the next cycle, you give a valid and the associated count,
Hmm.
right? The only problem or the only guarantee which you have to make is that the counter value which is given on the read side after the two transfers have been made, because this is a 64-bit counter, and in order to read the actual value you would need two transfers on this particular interface, right? So once the entire 64-bit value is seen on the read side, it should represent the actual value when the first request was made.
Hmm. Hmm.
So because we don't know when the counter is getting incremented or decremented, but whenever the request comes in, it should be a single atomic copy for the request on the output side, where basically the 64-bit value that means it is the actual 64-bit value which was when the first request was seen. Does that make sense? I'll try to explain it via an example. Let's say when the first request comes and the counter value was 0x, all Fs.
Hmm.
So this would be given as the output because this would be the 32-bit value of the counter,
Hmm.
right? So
Hmm.
you give that as an output, and the read side sees that hey, it is all Fs.
Hmm.
And now let's say then after a few cycles, the request again comes back to read the remaining 64-bit value of the counter. But by the
Oh.
time the request comes, the counter has already incremented to a value of, let's say, 1 followed by 000C, something like that.
Hmm.
So the output which would be given by the counter would basically be these 32 bits, which is bit 32 down to 63.
Hmm.
So it will give that as an output, which is fine, correct. But on the read side, what it will seem is that the actual value of the counter is 0001. Basically, bit 32 would also get asserted alongside all the bits here being 1. Does
Hmm.
that make sense? Right? Because the counter had incremented when the second request came in. So basically, that made the value of the counter to get flip over from this to be 1, and then this is what gets reflected. Now, if you take a look at the value which is on the output, it has a lot of error in it, right? Because all of the bits 31 down to 0, they do not match with the current value of the counter, which is 1 followed by 7 zeros C.
Hmm.
But the actual value which is seen on the read interface is 1 followed by all Fs. So we
Hmm.
want to avoid something like that to happen, which is why the the request here expects you to maintain a single copy atomic operation, which means that whenever the request came in, at that point you should capture all of the values and give that as the output.
Hmm.
So how would you design this particular module? You could,
Okay.
yeah.
Yeah. Let me try to
Hmm.
re-describe the question again in
Sure,
my own understanding.
sure.
So, just for the sake of understanding, let me take a smaller value of the, like, yeah, let's make it an 8-bit counter. So, is it of like every cycle the counter is going to increment? It's a free running counter, or the counter
Uh,
only.
No, so let's say that it gets incremented with certain events happening internally. So you don't know when it will get incremented.
But when I design this counter, I have to make it increment, right?
Yeah, so let's assume that you get the output, like the 64-bit output somehow here.
Okay.
Yeah,
So I'm basically not designing a counter. I'm just designing the logic to capture the count value.
correct. Yes.
Okay.
Hmm.
Um, okay, so I get an so it's an 8-bit counter, and
Hmm.
my interface is 4-bit wide.
Sure. Hmm.
So when I get a request, uh, in some cycle I get a request. So
Hmm.
in the next cycle, I'm returning the bit 3 to 0 of the count.
Hmm.
So I get a request in cycle 0. In cycle
Hmm.
1, I will return bit 3 to 0 of the count. And then I will only return. So then for me to return bit 7 through 4, I have to have another request. So
Correct.
one request will not return two values.
Yes.
Okay, both of them. Okay.
Yeah.
So there could be a situation where I get a request, and at that time, my counter was 8-bit, right? So like, it will go all the way from 00 through FF.
Hmm.
So I could be at count 1F when I got
Hmm.
the request.
Hmm.
So I got the request in the cycle, in this cycle. At that time, the count was 1F. In the
Hmm.
next cycle, I will return F.
Correct.
And I so when I'm returning that F, my request has deasserted. It was just a pulse for one cycle. By then, my count has incremented to 20, hex 20.
Right.
Now, then, yeah, it is just counting whatever. And then in this
Hmm.
cycle, I get another request.
Hmm.
So I should not return 2. I should still return, because I returned F previously.
Mhm.
I should return 1.
Exactly. Yes.
Okay.
So at this point, when the second request comes, the output on the next cycle should be 1,
Mhm.
because that would mean that the actual value of the counter seen on the interface would be 1f, which matches with the value which was here.
So I'm thinking that when I get the request, I should sort of like buffer this upper bit somewhere. I mean,
Mhm.
um, yeah, or I can put the whole 8-bit count in a buffer and send out request. Like anyway, if I'm responding in the next cycle, the output is a flopped version of the count, right? Like I'm not
Right.
directly combinationally reacting to a request. Um,
Mhm.
so I have to yeah, sort of latch on to this value. Uh,
Mhm.
and I have to know that when the next request comes, then it is not a request for this count, but it is a request for the MSB, like, yeah, MSB portion of this count.
Mhm.
Let me think. This is my counter.
Mhm.
And and let's say I have a buffer here.
Mhm.
Um, I use the request as the enable to capture the count.
Okay.
I mean, yeah, this is the count. I
Mhm.
then my output interface is only mm, four, half of it, like 32 bits, or in this case 4 bits. So,
Mhm.
but how do I know? I mean, maybe I have to keep like some flag to say that I have sent out the whole count, or because like when the next request comes, I need to know that if I'm using request as a enabling here, then
Mhm.
when the next request comes, I can't latch on to the count at that time, right? I need to know that that request is for me to send out the upper bits and not for latching on to the next count. So the enable here can't be just request, it's request and uh, the whole, yeah, basically like the whole
Some
previous,
flag.
yeah, some flag, exactly.
Mhm. Mhm.
That's what I'm thinking. So, hmm.
So,
So
by the way,
how?
you would also need that particular flag to differentiate between the upper half and the lower half.
Correct. Yeah,
Mhm.
I would need that. Um, how would I do this? How would I pick up, like, design the flag? Uh,
Yeah. So initially you would know that it is always for the lower half, right?
Correct.
So whatever that particular flag value is, that should, let's say it says 0 at that particular point of time. And by
Mm-hmm.
the way, we only need like a 1-bit flag there because we just need to differentiate between the two halves, right?
Mm-hmm.
And how that particular flag would work is that whenever you get a request, you just flip that flag to 1.
Mm, mm,
And then
mm.
you keep on doing it as and when you get the request, incoming request.
Yep. Yeah, that makes sense. So I get the first request, first time. That time my flag is 0. When
Right.
my flag is 0 and a request comes in, then I know that I need to latch on to the count,
Correct.
and I also flip the flag.
Yep. Hmm.
Now my next request comes in, my flag is 1. So
Hmm.
I need to, like, I mean, I cannot enable to latch on to the next count. I do still need to flip the flag, but my flag is 1 and a request has come in. So that means I have to send out the other portion of the count.
Right. Yep.
Yeah. Okay. Okay. So this is the request that is coming in.
Hmm.
Um,
Yeah, so I think yeah, this particular problem already has like the flag implemented for you, but I think we can implement it internally also. Let's
Okay.
not use the input atomic underscore I as the flag. Yeah.
Sure. So let me just call it flag. Um,
Okay.
Now, every time my request comes in, every time
Hmm.
a request comes in, the flag toggles, right? So
Hmm.
it's basically just a toggle flop.
Okay.
Uh,
Hmm.
right? Um,
Right.
Now I need something to capture my count.
Hmm.
Uh, so I'm saying that now my enable
Hmm.
is request has come in and the flag is 0. That is the
Right.
time I capture the current count.
Hmm.
Okay.
Yeah, I
Now,
think the current count is called count underscore q.
okay,
Or
okay, sure. Yeah.
yeah. Mhm.
Okay. Now I have to
Get
assert
the output.
valid in the next
Hmm.
cycle whenever a request comes.
Hmm. So I think it's called acknowledgement here.
Echo. Okay.
Yeah. Yeah.
So I can just, I'm thinking, it's just a flopped version of the
Sure.
request.
Sure. Yeah, I think we would skip that and just move on to the
Okay, sure.
actual count
Um,
output.
so if my count O will be, if my, so what's happening here is, uh, a request came in that
Hmm.
that was the first request. My flag was 0. My flag flipped, became 1. That means that in that cycle where the flag has become 1, a previous request has come in. So in that cycle, I'm sending the lower half of the count, right?
Correct. Correct. Yep.
So so basically, when I have a ACK O, when my
Hmm.
output is valid and my flag is 1, then I'm sending uh 31 to 0.
Hmm.
Otherwise, or maybe like I should check ACK O if I flag, or I can just, yeah, I can just do what I was doing. Um,
Hmm.
Otherwise, I mean, I still need an ACK.
Hmm.
My flag is 0. Then it's basically, there's probably a better way to do this, but this is what is coming to my
Sure.
mind right now. So,
No, I think it's
uh,
fine.
otherwise, what is the count? Like, if there is,
I think it expects it to be zero, so we can probably do
okay,
that. Yeah.
or sorry, 32.
Right. Cool. Yeah, I think this would work. Yeah, the only question I have here is that do we really want to store the entire 64-bit counter value, or can we just store, let's say, the MSB part of it and be done?
Hmm. Hmm. Um, so I mean, because I'm because there is a one cycle latency between when the request comes in to
Mm-hmm.
when I'm responding with the count,
Mm-hmm.
right? So if the request comes in, I cannot directly respond from the counter output. How do I, like,
I
if I'm
mean,
responding in the next cycle, then in the next cycle the count could have incremented, right? Even the lower portion of the
right,
count.
right. Which is fine as long as we maintain the single copy atomic
I
sort of
see.
version, right? Yeah. So as long as let's say it wouldn't matter if the count was 1E versus 1F, but we should not do, if it was 1F and then we are giving out as the problem statement which we explained before, that the count actually comes out to be as 2F because it got incremented and stuff like that. So
But
that way, I think. Mhm.
even in that case, I mean, I'm just thinking out loud here, but
Sure.
let's say the count is 1F, right? And I only
Hmm.
latch the upper portion of the count.
Hmm.
Uh, so the request comes in this cycle.
Hmm.
Uh, then I'm responding in this cycle. So when
Hmm.
I'm responding, I'm going to give out 0 at this point.
Correct.
So
Mhm.
actually, then 2 is what I have to latch on to.
Correct. So the latch logic would also change. So it will
Yeah.
all depend on when you are sending your, I mean, when you are picking out the 64-bit value or the
Yeah.
8-bit value in this case. Yeah.
Yeah. So in this case, then I will not use the request to latch onto it. I'll use a flopped version of the request or the ACK,
Correct.
basically, the first ACK that's
Exactly.
going out. That would be my enabler. And then I can only latch onto the upper portion.
Yes. So that actually saves like quite a few
Yeah.
flops, right? 32 flops here. So
Hmm.
that's fine.
Yeah, I see. Okay.
Okay.
Yeah, that makes sense.
Sure. Yeah. So yeah, first of all, thank you so much for taking out time and doing this mock interview with me. Do you have any questions or any feedback to share?
Uh, no, I don't have any particular questions at this
Mhm.
time. I think having the platform to code was really helpful. It's a
Sure.
very nice platform, and yeah, and I also really liked that you asked me in the round robin arbitration, you asked me to, show the critical path, because I
Mhm.
think that's very important as we design to think about what's our critical path. So,
Right.
yeah, thank you.
Uh, Yeah, thanks for that. And I think one thing which I would like to mention is that I really like your approach of working towards the problem, especially that the first thing which you do is to, walk through your understanding of the problem statement, and that is very critical because a lot of times interviewers they sometimes miss some of the tiny details, and if you walk through that, you try to figure it out together, which is something which I actually enjoy when the candidate does that. So that was good, and I think yeah, liked the way you coded each of the segments of the RTL, where you were explaining what you were trying to do next and how you were planning to do it. So that always helps keeping the interview engaging, and it helps me also to understand, hey, okay, this is what you have coded, instead of you first writing the entire code and then trying to explain
Hmm.
it. So
Hmm.
yeah, so I like that. Yeah,
Thank you. Thank you for that feedback.
sure. Yeah, thanks and all the best.
Thank you.